All right, good morning, everybody. I hope you all had a good weekend because you will need that because now we are going to the last few weeks of classes. So this would be a bit tedious for you guys because submissions of final reports or exams will be coming up. So let's go on and look at. I think you already finished section 9.8 today. What I plan to do today is to work on section 9.7, which would be some exercises on power series. And then hopefully on Wednesday, we can start with section 9.8, Taylor series expansions. And then hold on, what's after that? Let me take a quick look at your textbook. Oh, I guess section 9.8 is the last section in Cal 2. Is that correct? Let me see. Oh, we still have chapter 10, which is polar coordinates. I thought we're done, but we still have chapter 10 apparently. All right. So today let's do power series. Well, power series are of the form sum of say a sub k times x to the power k, or sum of a sub k x minus a to the power k. So these are power series, and the difference with the series that we worked on last week is that now this series involves the variable x. So you can think of this as functions on their own, right? So this is a more complicated type of function because it involves the variable x. And since there are variables x now, the convergence or divergence of this power series will not only depend on how the factors involving just the value, the number k, which is the index of the summation, but also on the values of x. So just to make it clearer, here I'm summing up, say, from k from 1 to infinity. Actually, it doesn't matter what the starting k value is, as long as it is finite, right? So here, the convergence or divergence of this series will be determined by the value of x. That's why we have what we call the interval of convergence. This would be the set of all x's for which the power series is absolutely convergent. Because we love to work with absolute convergence rather than just merely convergence. Because the thing is that I don't know if it was mentioned before, but if your series is absolutely convergent, then you can rearrange the terms in your series and you will get the same sum. But if it is just if it's conditionally convergent, then you can rearrange the terms to get any number that you want, or rearrange the terms in the series to get any number that you want. But that's the technical reason why we are more interested with absolutely convergent series, in particular power series. So basically, our goal now is to look for the values of x for which this series will be absolutely convergent. I can think of three tools that we can use in order to determine this interval of convergence. The first one would be check if the power series is geometric in form. Okay, because if it's geometric in form, it will look like summation of a constant times x to the power n, right? Or yeah, the sum will go from n to pos to one from 0 to infinity, right? So if your power series is geometric in form, that means you have constant multipliers to powers of x's, then you can use the geometric series test, right? Here, the common ratio is equal to x, so the interval of convergence is simply given by Remember, when our geometric series convergent, they will converge if the absolute value of r, in this case my r is x, would be less than 1, right? So that would be the interval of convergence for power series that are geometric in form. But in most series, you can use the ratio or the root test. But a little caveat here, remember that the ratio and root test requires that the limit would be less than 1, right? That means automatically convergent. So x values for which the limit is less than 1 belong to the interval of convergence. Let's call the interval of convergence IOC, right? And then when L is equal to 1, you need to plug in the x value in the series and perform other tests. So this would be our general framework in order to find the interval of convergence of certain series. So perhaps this will all make sense if we look at specific examples. So I have in worksheet 19 the exercises from the textbook. So I just copied them over here. So you'll have lots of problems to practice on. Let me just use these examples I got from the Lamar tutorial, I think by Paul Dawkins in the net. I think I shared this link via worksheet 17, I guess. So you can visit his materials there. They are very good. So yeah, they are good reads. So let's borrow some examples from him. Let's start with number 1. Oh, the instruction here is to determine the interval of convergence for the following, right? So first series would be sum of x to the power 2n all over negative 3 to the power n. As n goes from 1 to positive infinity. For this, you can use the root test. You can also use the ratio test to find what are the values for x that belong to the interval of convergence. But what we can use here would be to recognize that this is a geometric series, right? So this is a geometric series with common ratio r equals what? Well, I can rearrange this 1 to positive infinity, write it as x squared over negative 3 to the power n, right? So I have a common ratio here. A sub k is a constant. It's a constant 1, so a is equal to 1. Common ratio would be x squared over negative 3, right? And so this will converge if and only if the absolute ratio or the absolute value of the common ratio, which is x squared over negative 3, would be less than 1, right? But here we can solve this inequality. We can say that this would be x squared over 3 less than 1, implying x squared is less than 3. Okay, so this means that what? This means that x squared, that x is between negative root 3 and positive root 3. Okay, let me just check one thing here. I think I realized I made a mistake in one of my in my other class, but let me see. I see that you guys are having fun at the chat. Okay, let me see. Okay, so that's it. It's a geometric series, so the interval of convergence is equal to negative root 3 comma root 3. Yeah, I just realized I made a mistake in my other class, but anyway, I'll just correct it later with them. All right, so this is the interval of convergence. No more tests to do because this is already because this is geometric in form, and we know that geometric series will only converge when the common ratio is less than 1 or is strictly less than 1. All right. Okay, I see Daryl has a question here. Hold on. Maria has a question with this. What do you mean test them, Maria? Do you mean the endpoints, root 3 and negative root 3? If you use the ratio and the root test, you would have needed to check at the endpoints, because at the endpoints at negative and at plus or minus root 3, the limit when you take the ratio, then you will get equal to equal to 1. So you need to test them. But here I didn't use the ratio or the root test. I use the fact that this is a geometric series, and I know that geometric series will be divergent when the common ratio is equal to 1. So yeah, I'm using geometric series test here. Then I don't need to check the endpoints because geometric series won't converge at the endpoints. But you're right. If you're using the ratio or the root test, you would have needed to test at the endpoints, and we'll see some examples of that later. All right. Let me just segue a bit to Daryl's question. Okay. Yeah, for your question, Daryl, John is correct. You just need to take the limit and see which doesn't approach 0. And that's where the basic divergence test will tell you that this would be divergent. So for instance, the first series is sum of 1 over n, but 1 over n goes to 0 as n approaches infinity. So you cannot conclude divergence using the divergence test, right? Then for number 2, you have root n over, or sum of root n over n plus 10. The top has degree or has highest exponent 1/2. Denominator has highest exponent 1. Denominator wins, so the limit here is 0. No conclusions by the BDT. Now, if you look at part C, what is part C? A to the n all over n cubed. If this is option C, you can use L'Hopital's rule here because this would be infinity over infinity. And then you'll see that the limit would be, I think, positive infinity, because we also have a shortcut here. The numerator is an exponential function. The denominator is a polynomial. Exponentials grow faster than polynomials. So top wins, the limit is equal to infinity. So the limit is not equal to 0, so therefore this is divergent by the basic divergence test. All right. If you go to part D, that will go to 0, so BDT has no conclusions. And then for part E, the denominator is a factorial, so it grows faster than a polynomial, so the limit of the n term in option E is 0, so BDT won't apply either. So the answer here is part C, because it is the only one whose limit is not equal to 0. All right, is that good, Dara?
Yes, thank you, Neil. Thank you, John.
All right, you're welcome. Okay, all right. So let's go on to the second problem here. Let's see. Let's have sum of negative 1 to the power n over n, negative 1 to the power n times n over 4 to the n times x plus 3 to the power n. The starting value for n doesn't matter, so I'll just leave it there. So let's find the interval of convergence here. Well, here you can use either the ratio or the root test because it is not geometric. you will see that it is not geometric because the common ratio, if you will treat this as a geometric series, the common ratio is the 1 raised to n, right? So if you collect all the factors that are raised to the power n, you will get this guys. But the remaining factors that would observe as your a is not a constant, but they depend on the variable n, right? So it is not geometric in form, so I cannot use the easy test, the geometric series test. So here I'll use the ratio test. So actually not just the ratio test, but the absolute version of the ratio test. So I'll take the limit of the absolute value of a sub n plus 1 all over an as n approaches infinity. I'll evaluate this limit and later compare it to 1, right? So if I'll do this, I'll have limit of the absolute value of, I'll replace all n's by n plus 1 all over 4 to the power n plus 1 times x plus 3 to the power n plus 1. And then supposedly it was a division by a sub n, right? So I'll right away turn it into a multiplication problem by the reciprocal of the n term. So it's going to be 4 to the power n all over negative 1 to the power n times n times x plus 3 to the power n as n approaches infinity. All right. Now, let's see. Actually, the negative ones will not matter, right? The powers of negative 1 won't matter because we are inside absolute value. But if you want to be strict about it, if you do the cancellation here, you will have a negative 1 left. But that negative 1 is inside the absolute value bars, so that won't matter anymore. So you'll have a positive 1 instead. And then we'll cancel 4 to the power n by the denominator, which will leave us with a 4 there. And then x plus 3 to the power n here will all be canceled by the power of x plus 3 on the top, but we'll have 1 left on the numerator. So if I'll collect all that remained, we'll have the limit of n plus 1 all over 4n times x plus 3 with absolute values as n approaches infinity. I was able to free this factor out of the absolute value because it's always positive, right? When n goes to infinity. So this is always positive, no need for the absolute value. But I need to keep the absolute value for x plus 3 because x plus 3 can be positive or negative depending on the value of x. So that's important. X's never come out of the absolute value because we are not sure whether it's positive or negative. Unlike n plus 1 over 4n, I know that that is positive because n is a positive number, right? Okay, and when we evaluate the limit, remember, we're taking the limit as n approaches infinity. So x plus 3 is independent of n, so you can treat it as a constant with respect to the limit. So it will come out of the limit. And then we'll just be left with the limit of n plus 1 all over 4n as n approaches infinity. But what is the limit of this limit? Well, numerator is degree 1, denominator is degree 1, equal powers, so that means we just divide the coefficients. So the limit would be 1 over 4, right? Okay, and that's the limit. Now, remember the ratio test. The ratio test tells us that the series will be convergent if the limit is equal to 1. So for convergence, we want the limit to be less than 1, right? So that means we set the limit, which we found out to be the absolute value of x plus 3 all over 4 to be less than 1. Then I can multiply both sides by 4. I'll have absolute value of x plus 3 less than 4, and I will solve this inequality in X, right? So first, I want to get rid of the absolute value, but since this is a less than inequality here, this can be a continued inequality, negative 4, x plus 3 less than 4. Then I want x to be isolated in the middle, so I subtract 3 from all sides. So I will have negative 7 less than x less than 1. So the series absolutely converges on negative 7 to 1, right? But we're not done yet. I'm not saying that this is the interval of convergence. I'm saying that I'm sure that if x's are strictly between negative 7 and 1, it's absolutely convergent. But I am not sure if it would converge or not at the endpoints, because remember, the ratio test is inconclusive when the limit is equal to 1. And it happens at the endpoints negative 7 and 1. So we know that if your number lies strictly between negative 7 and 1, it's absolutely convergent. If it's if x is equal to negative 7 and 1, we don't know what will happen at this point, right? But if it is something that is less than negative 7 or greater than 1, we know it is divergent right away. So only 2 tests remain here. We need to check if the power series is convergent at x equals negative 7 and 1. And for that, we need to check them individually. So here, let's see what happens if x is equal to negative 7. We look at the given series. So this is the given series. Okay. Then all we need to do is to replace x by negative 7. So the x here will become negative 7. And then when we simplify, this would be negative 1 to the power n times n over 4 to the power n times negative 4 to the power n. Right? And then I can multiply this, and it will become 4 to the power n times n over 4 to the power n. The 4 to the power n's will cancel each other out, so we'll be left with the summation of n's. So that means when x is equal to negative 7, the series simplifies to the sum of n, which is divergent by what? What test did I apply? Do you remember, guys? Why was I able to conclude that this is divergent? Or there could be more than one test, but not exactly the ratio test, Maria. I'm referring to this guy. How do I know that the sum of n is divergent? If you will apply the ratio test here, you'll have limit equal to 1. So ratio test is inconclusive. And we know that right away because that's the reason why we are testing at x equals negative 7, because the ratio test is inconclusive. Herson is correct. That's what I'm looking for. This is divergent because of the basic divergence test. You take the limit of n. As n approaches infinity, that's infinity not equal to 0. So it's divergent by the basic divergence test. All right, so we know that this will diverge at x equals negative 7, so it's out of the IOC. Now the other one is if x is equal to 1. That's the other endpoint at which we knew that the ratio test was inconclusive. So let's look at the given series again. Plug in x equals 1. So here we'll have sum of negative 1 to the power n times n, 4 to the n over 4 to the n, which simplifies to sum of negative 1 to the power n times n, all right? Which is also divergent. Why is it divergent? You can also use the BDT, right? Because here n will not approach 0, So that means the limit of -1 to the power n times n will not exist because it will just be oscillating between a large number and a small number. So definitely the limit is not equal to 0. So by the BDT, it is not divergent. It is not convergent. All right. So we now conclude that with certainty, the given power series will be divergent at the endpoints. So therefore, we can say that the IOC is the open interval -7 to 1. All right. Any questions or clarifications with that?
Hey Neil, I have one question.
Sure, go ahead.
So in the step where you were going to take the limit of what we got, and you realized that we had equal powers in the numerator and the denominator,
Uh-huh.
if the numerator was larger, the denominator was larger, could you do that same thing where you compare the powers, or would you just went ahead and took the limit?
You mean if you have, say, the limit of, say, n to the fourth plus 3 over -3n to the fourth, something like this?
Something where if they're different. So like that
Oh,
one
where
was
they're different.
a third, right?
Okay. Mm-hmm. So for instance, here you have power, say, to the fifth, something
Yeah.
like this.
Mm-hmm.
Mhm. Yeah, so here you compare top and bottom. So here they are not equal, so you cannot divide the coefficients. You only divide the coefficients when they have equal powers. But here the denominator has a larger power, so that means the denominator grows faster than the numerator. So that means the limit is equal to 0,
Okay.
right? Or you can say, okay, the highest power here is n to the fifth. What's the coefficient of n to the fifth on the numerator? It's 0, right? Because there's no n to the fifth in the numerator. In the denominator, it's -3. So 0 divided by -3, the answer is 0. So the limit is 0.
Okay.
That's another way of looking at it. But I guess the simpler explanation is that the denominator has a higher power, so the denominator grows faster, so the limit would be equal to 0.
Okay.
But if it happens that the numerator has a higher power, say n to the 8, so that means the numerator grows faster. So here the limit would be positive infinity.
Okay. And it would be -infinity if it had a negative coefficient in the numerator?
Actually, here you will have a negative infinity because I forgot that my denominator is negative.
Okay.
But for us, that doesn't matter because the BDT just say if it's not to 0, then it's divergent right away. Right.
Okay. Thank you.
All right. Okay, let's see. All right, other questions? None? Okay, let's try one more. It's odd that you guys didn't bring lots of questions today. So was the lesson easier today, or you just haven't tried the exercises yet or the homeworks yet? Oh, you have given up? That's not a good choice, Arsalan. Oh, hopefully, Maria, you're not spacing out today in the lab. So just let me know if you want to have some clarifications with some of the problems. But I hope you are following today because it's just an application of the ratio test or the root test with just some modifications or added steps. All right, that's fine, Daryl. Take your time, but be mindful of the deadline. I can still help you with some of the problems on Wednesday, so don't worry. So let's just keep on going and answer some basic examples. Oh, really, Hersa? Not a fan of this chapter? Way back in the day when I was an undergraduate, I also hated this topic on series because back then what I just did is to memorize or try to memorize the tests, the conclusions, and everything. And you know me, I don't like memorizing things, so I didn't appreciate it back in my undergrad days. But when I started teaching, I understood what's the theory or what's the reasoning behind this test. So it is now more natural to me. So yeah. Okay, so let's try problem number 3 before I'll go to Morel's question. Okay. So for number 3, all right, so we have factorials and we have powers n. So here, perhaps I'll use the ratio test. Because again, ratio tests are extremely helpful whenever you have factorials and even powers. The root test won't help you with factorials, so we'll stick to the ratio test here. Again, we take the limit of a sub n plus 1 all over an with absolute values this time as n approaches infinity. All right. Then I'll have limit of n plus 1 factorial times 2x plus 1 to the n plus 1, right? So I just replaced all n's by n plus 1 all over. I'll just copy the term in the series. But remember, everything is inside the absolute value bars. Okay, now we know that n plus 1 factorial will cancel with n factorial, but it will have some change. Specifically, you'll have an n plus 1 left on top. Meanwhile, for those with the 2x plus 1, the entire denominator will be wiped out, but there will only be a 2x plus 1 left in the numerator. So basically here, we'll have the limit of the absolute value of n plus 1 times 2x plus 1 as n approaches infinity. Remember properties of absolute values. This guy is always positive, so it can come out of the absolute value. Then we'll have absolute value of 2x plus 1 as n approaches infinity. And then this guy would be the limit as n approaches infinity of, okay, I'm taking the limit as n approaches infinity. It's independent of x. So 2x plus 1 will come out of the limit. We're taking the limit of n plus 1 as n approaches infinity. And this would be infinite or positive infinity, right? Whenever x is not equal to minus 1/2, right? So let's see why, because I think it's clear that this limit is equal to positive infinity. But be mindful that we have an absolute value of 2x plus 1 here, right? So if x is equal to negative 1/2, this guy will be 0. So we'll have 0 times infinity indeterminate. So I don't have any conclusion for that. But if x is anything beside negative 1/2, then the limit is surely equal to positive infinity. So that means the only the only point where the power series can converge is x equals negative 1/2. I'm not saying that it will be convergent, but I'm saying that by the ratio test or by taking the limit, the only possibility of convergence here is when x is equal to negative 1/2. All right. Now we need to test that if it's convergent really on negative 1/2. So if x is equal to negative 1/2, what do we have? Well, I look at my series. Oops. Okay. So if I replace x by negative 1/2, I'll have sum of n factorial times 0 to the power n. But 0 to the power n is equal to 0. It's not a limit. So pay attention with this, because this guy, the base will exactly be 0 when x is equal to negative 1/2. X is exactly negative 1/2. It is not something approaching negative 1/2, but it is exactly negative 1/2. So the base here is an exact 0. You have an exact 0 raised to any power, however big it will still be 0, right? And then 0 times any number, be it a factorial, however big that other factor is. This is an exact 0. So that means this will just be sum of zeros. And if you sum up infinitely many exact zeros, then the sum would be 0. So we can say that the interval of convergence is only the point -1/2, which is, let me put this in quotes. It's not technically an interval because you only have one number, which is -1/2. So the radius of convergence is 0 because you cannot form any interval because you only have a singleton or a single number at which this power series will converge. Actually, it will just converge trivially because you're summing up infinitely many zeros. Okay? Is that clear, guys? And I hope by now it's clear what's the difference between taking the limit or working with numbers that are very, very close to 0 and exact 0. All right?
Hey, Neil, a quick question.
Sure, go ahead.
So you solved to find what x would equal with that limit because why?
All right. So is this clear until this point? I hope it's clear. All right.
Yes.
So when I look at this limit, when n approaches infinity, this guy will go to infinity, right? So
Mm-hmm.
that means this limit is infinity,
Mm-hmm.
right? So the thing here is if this guy, because x is a variable, x can take any number.
Mm-hmm.
So for if 2x plus 1 happens to be any other constant except 0, I have a constant times a large number, it will still be a large number.
Mm-hmm.
But be careful, because when x is equal to -1/2, this is -1/2. This would be 0, right? When x is -1/2,
Mm-hmm.
0 times infinity, it's indeterminate.
Oh.
Actually, it won't be indeterminate because here, this is an exact 0. When x is equal to -1/2, 2x plus 1 is exactly 0.
Mm-hmm.
And if you have an exact 0
And that,
times a large number, the product will still be 0, right?
oh, okay. Okay.
Okay. So that's
Oh,
why I need to be careful with x equals -1/2 because it will give me a convergent series, which is quite trivial because the sum is just 0, but nevertheless it's convergent by definition.
okay. Thank
All
you.
right. Okay. Now, as I promised, let me go to Merle's question. Yeah, Herson is correct. I guess here you need to use the um, the ratio test. Let me just do it here. So you have sum of k cubed over 2k plus 1 factorial. Though you need to be a bit careful with the factorials there. So you take the limit of, since you're just working with a series, no absolute values are required. So this would be the limit as k approaches infinity of, replace all k's by k plus 1 all over 2 times k plus 1, everything inside the factorial, right? Because that k was multiplied to 2, then added a 1. So that's all. That's also what we do, but instead of a k, we'll do a k plus 1 times the reciprocal of the original series, original term. So we'll have 2k plus 1 factorial on top, all over k cubed. All right. Then we evaluate. So I'll just put this guy and this guy together in a single fraction. So I'll have k plus 1 all over k to the power 3, loss of exponents, times the factorial. So I have a 2k plus 1 factorial here, all over, when I simplify this, I'll get what? 2k plus 2 plus 1, so plus 3 inside a factorial. And then some things will cancel up here. 2k plus 1 will all be canceled, but in the denominator, what will we have? What we will be left with 2k plus 3. It won't be canceled. 2k plus 2 won't be canceled. 2k plus 1 won't be canceled. Oh, 2k plus 1 will be canceled because here, this guy is a product until 2k plus 1. So 2k plus 1 will be canceled. So we'll be left with this. So this is the limit of k plus 1 cubed. Let me just write it there. All over k times 2k plus 3 times 2k plus 2 as k approaches infinity. And now at this point, we know that the numerator is degree 3, right? And then the denominator is also degree 3 because there are 3 k's in there. So we just need to divide coefficients. So the coefficient of k cubed in the numerator, when you do the expansion, it will just be 1, right? In the denominator, what's the coefficient of k cubed? We have k times 2k times 2k, so that's 4k cubed. So it will have a 4 there. So the limit is 1/4, which is less than 1. So by the ratio test, that will be convergent. Okay, Morel? All right, so I hope that's clear. Okay, person sent the question. Okay, determining whether that is absolutely convergent, converges conditionally, or divergent. Okay. All right. So your person was stuck in showing that this is decreasing. Well, you can rearrange some of the terms because you need to check a sub n, right? If it's decreasing. In this case, a sub n would be 5 to the power 2n plus 1 all over 2 to the power 3n plus 2. We can write this as what? I can write it as 5 to the power 2n times 5 all over 2 to the 3n times 2 squared, right? So I'll just split them up. Here I'm just playing with the exponents to be able to write it in a more in a simpler manner, or in a manner that is more obvious that it will increase or decrease. All right, so we have that. And then so I'll have a 5 over 4 from this guys times, I'll play with loss of exponents again. I'll have 5 squared over 2 cubed raised to the power n. All right. So this guy would be 5 over 4 times 25 over 8 to the power n. All right. And what can we say about 25 over 8 to the power n when n increases? The thing here is 25 over 8 is greater than 1. So when you raise something greater than 1 to a power, to a large power, you will get a larger number, right? So that means this is increasing. Because when n increases, 25 over n to the 25 over 8 to the power n will also increase. Actually, in this problem, person, it would be divergent because the limit of an as n approaches infinity, and I guess it's much better to see now, would be the limit of 5 over 4 times 25 over 8 to the power n as n approaches infinity. You have here a number greater than 1 raised to a very large number. It will go to positive infinity. So by the basic divergence test, this will diverge. Hopefully I did all the calculations right, but I hope you see the idea. All right, so perhaps can you still change your answer for the e-homework? I hope you can. Oh, Daryl, you have a question?
Hi, I was just gonna ask just to confirm. So for this part of the test that we just used, if it was like 8 over 25 to the n, it would be less than 1, and therefore you can say it would be decreasing?
Right. So if your an was, say, 10 times 8 over 25 to the power n, this is something less than 1. But whenever you have something less than 1, if you raise it to a large power, this would be decreasing.
Okay.
For instance, you have 1/2, right? 1/2 to the power 1 is 1/2, but 1/2 to the power 2 is 1/4. And 1/2 is larger, definitely, than 1/4.
So it'll be getting smaller and then decreasing.
Yeah.
Okay. Thank you.
So something less than 1, you raise it to a large power, it would be a smaller number. All right?
Thank you.
Okay. And the limit will be equal to 0 for an if the base is less than 1. Because if you keep on increasing n or raising a fraction less than 1 to a large exponent, then the limit will be equal to 0. All right, so let's see. No more questions. Let's try another example. Let's see. Let me just erase this. Okay. Let's try problem 4. I was thinking to start with power series expansions, but I don't think we'll have time to finish one big example on that. So let's try this one. Sum of 2 to the power n all over n times 4x minus 8 to the power n. Okay, so here let's try this one. Let's use the ratio test again. Though you could have also used the root test here. So let's take the limit of the absolute value of an plus 1 over an as n approaches infinity. So for the first factor, I'll just replace all n's by n plus 1. Times the reciprocal of an. Basically, this would be n over 2 to the power n times 4x minus 8 to the power n. And let's do the cancellations. So the entire 4x minus 8 power in the denominator will be gone, leaving us with only a single one in the numerator. And then 2 to the power n will be canceled, leaving us with a 2 in the numerator. And I guess that's it. Limit as n approaches infinity. We'll have the limit of the absolute value of 2 times n times 4x minus 8 all over n plus 1. But since this factor doesn't have an n in it, it can go out of the limit. So I'll have absolute value of 4x minus 8. Don't forget the absolute value, putting it there, enclosing 4x minus 8. And we'll have the limit of 2n over n plus 1 as n approaches infinity. Equal powers. So that means I'll just divide the coefficients. So this would be 4x minus 8 times 2, right? Because this limit will just be equal to 2. And again, we want the limit to be less than 1. So we'll have 2 times the absolute value of 4x minus 8. We want it to be less than 1. And then I can divide both sides by 2. Did I do the calculations right? Yeah, I think so. 2n left. All right. So here we'll have a continued inequality. We'll have a negative 1/2. 4x minus 8 less than 1/2. And then I'll add 8 to all sides. So here I'll have what? 8 minus 1 over 2 less than 4x. 8 plus 1 over 2. So I'll guess I'll have 15 over 2 less than 4x less than 17 over 2. And then I'll divide all sides by 4, giving us 15 over 8 less than x less than 17 over 8. So here, we know that the power series will converge on the open interval 15 over 8 and 17 over 8. But we don't know what will happen at the endpoint. So we need to check at the endpoints. So when x is equal to 15 over 8, let's see what happens. Let me copy this guy. And I replace x by 15 over 8. And I guess this would be what? This would be sum of 2 to the power n all over n times this guy would be 15. This would be 15 over 2 minus 8. So that's going to be negative 1/2 to the power n. And this would be the sum of 1 over n times negative 2 over 2 to the power n. So this would be sum of negative 1 to the n all over n. Okay, but what can we say about this series? This is convergent. Actually, it will be convergent by the alternating series test. Why? Because an is 1 over n, which is decreasing. And the limit of an as n approaches infinity will be equal to 0. So it is convergent by the AST. Okay? So at the left endpoint, 15 over 8, the series will be convergent, right? So be sure to include it in the IOC. On the other hand, if x is equal to, what was the other endpoint? 17 over 8. Okay. If you plug in 17 over 8 here for x, so we'll have 4 times 17 over 8. So we'll have sum of 2 to the power n over n times this guy would be 17 over 2 minus 8. So that's going to be 1/2 to the power 2. And you see that this will be canceled by that, right? Because this will have a 2. This will have a 2 to the power n in the denominator. So basically, this will just be sum, of 1 over n, which is divergent because it's the harmonic series, which is divergent. So therefore, for this problem, the interval of convergence is the half-closed, half-open interval 15 over 8 to 17 over 8, right? So here I included 15 over 8 by virtue of putting a square bracket there because we have seen that the resulting series at that endpoint is convergent, but I kept a parentheses for 17 over 8 because there the series will be divergent because once we substitute x equals 17 over 8, we'll get the harmonic series. So that's why it's important to always check at the endpoints because they are independent of what happens in the interior and also of each other. So make sure to check the convergence of the series that you will get if you plug in the endpoints of your interval. All right. So on Wednesday, I'm thinking to talk about series expansions, which I guess would be a good bridge between 9.7 and 9.8. So we look at how to use a power series in order, or integration and differentiation of power series to obtain an expansion for certain functions. And then we'll move on to the more general way of getting a series expansion for functions, which is the Taylor and Maclaurin series. All right, guys. So, but again, if you encounter some questions on your homeworks or quizzes, just let me know on Wednesday. All right. Morel, I think I got your email, so yeah, I'll take a look at it later today.
Thank you.
All right. So that's it for today, guys. Thank you for coming today, and let's see each other again on Wednesday. All right. Bye, guys.